So now we're going to talk about how to constrain the stress polygon using information from both well-bore breakouts and tensile fractures. I already talked about how to constrain the stress polygon using information from drilling-induced tensile fractures. And now the focus will be also doing the same, but with data from well-bore breakouts. So we start again with this equation, which is Kerr's solution when small r, any radial distance from the centroid of the well-bore to the setting that's equal to the well-bore radius, right? And this is what you get for hoop stress. And when the hoop stress is equal to the rock strength at the stress conditions in the subsurface, then we form breakouts. And that will typically happen in the direction of SHmean, right? So typically this value is going to be less than or equal to the rock strength. At the point when it is equal to the rock strength, that's when you form the well-bore breakouts. And now we can make SHmax the subject of this equation. So transfer all the other terms to the right-hand side. Keep in mind SHmax also shows up here, which is why you're dividing by this value. And that gives you this expression for SHmax, right? We already talked about this before. This is the minimum hoop stress, again using Kerr's solution at r equals theta. Another point is this is at theta equals what? You see, now we're saying theta b, theta breakout. Theta for the breakouts. And again, it starts at the direction of SHmax up until you see the breakout. So that's your theta b. So that's one modification that has been made to the Kerr's solution. So theta is theta b, basically. And now we can talk more about theta b in terms of radians. So angles in radians, this is the expression to get theta b. In terms of angles in degrees, this is the expression for theta breakouts. And all it is that, let's do the one in degrees first. You already know this is 90 degrees line, right? This is the breakout width in degrees. So whatever that angle is, this total angle is, you can divide it by 2, right? So you get this. So this angle, which is theta, phi b divided by 2 plus theta b, right? Plus this equals 90, right? 90 degrees. Everything is in degrees. And so you can make this the subject of the equation, and what you get is precisely this. You see that? 90 minus theta b over 2. We can express it in radians, like I said, also. And in that case, we call that angle width of the breakout when it's in, although it doesn't really matter, right? You just need to know whether you're using degrees or pi radians. So for now, I'm just going to call it width of the breakout, which is what this is. And so this width of the breakout plus 2 theta b, right? This is theta b, this is theta b, will give you 180 degrees, right? And what's 180 degrees in radians? It's pi radians. So width of the breakout plus 2 theta b equals pi in radians. And that's precisely what this is when you make this is the subject of the equation. So it becomes pi minus width of the breakout. So now you see where those two expressions are coming out from. Good. Here, they use positive value for tensile strength, tensile rock strength. And in the previous version, we had seen minus. And like I said, that's only to indicate to indicate the sign convention. So because these guys are all positive, if you're going to use a positive value for the tensile strength, then you have to put a minus in front of it. Because tensile stresses are negative when compressive stresses are positive. But if you just write it as T, then it's up to you to put the negative sign in front of it if you have a finite value of tensile strength. But it's irrelevant when tensile strength is 0, which is the assumption in virtually all of these cores, because rocks are weak in tension. So we have discussed this before. I'm not going to talk too much about this. This gives you the constraints, and again, you just make SHmax the subject of the equation and you get this. And I already explained these two concepts, right? So we can move on to talk a little bit more about well-bore breakouts and what they look like. And as your well-bore breakout, this will be the width of the breakout. And the moral of the story on this slide is, with time, as you drill, the width doesn't necessarily widen out, because if the width widens out, then the well fails, because you have a general enlargement. What you have is a deepening. So the width remains the same, but as time progresses, it goes deeper and deeper into the formation. You see that? And this is an actual image showing that. So at this instant in time, this is where it used to be like this, right? This is the part that has failed. But further and further in time, it goes deeper and deeper into the rock. But you see this width of the breakout really never changed. And that angle is the width of the breakout. So that's the moral of the story there. The width of the breakout in degrees does not widen, but the breakouts can actually go further in the formation. And this will not cause too much of a drilling problem, right? As long as the general size of the hole in the other directions do not widen. And now, this is how we use the information from well-bore breakouts to constrain SHmax. We previously discussed this one, which is what? The drilling induced tensile fractures. So that equation I showed 2 slides ago, when you express it in terms of SHmax, that equation is the function of SHmean, right? And that's what gives you the line, because this is SHmax on the y-axis as a function of SHmean on the x-axis. So that's what you'll be plotting up actually in homework 4. Now, what are these lines? These are the equations for SHmax as a function of SHmean, and obviously width of the breakout. And that's coming from the Kirsch equation for well-bore breakout, the one you saw, the first equation where we set this guy to the rock strength, right? And now made SHmax the subject of the equation to get this. So these are the lines, but at different values of rock strength. So these are the rock strengths. So if the rock is relatively weak, the line is lower. If it's stronger, the line is at a higher level, meaning you're going to have to increase SHmax up onto this value or more before you can observe well-bore breakouts. So if you observe well-bore breakouts, you will be above this line. If you don't, you are below. And again, you have multiple lines because we are using multiple values of effective rock strength. And so the summary is we can use the breakout width together with those equations we saw 2 slides ago to further constrain the stress polygon. I already explained that these are different rock strengths and they give you different lines for different SHmax as a function of SHmean, which is precisely the equation for these lines. And in these lines, we have assumed that the breakout angle is 45 degrees. And like I said before, extremely important to know that if you don't observe drilling-induced tensile fractures, then you will be below this line. If you do observe, you will be above the line but still within the stress polygon. For this one, if we assume the rock strength is 110, if you observe well-bore breakouts, you will be above that line but still within the stress polygon. If you don't observe well-bore breakouts, you will be below the line, still within the stress polygon. And that's how we constrain the range of uncertainty on SHmax using information from well-bore breakouts and drilling-induced tensile fractures.